Hello everyone. In this presentation, we will talk about the clinical audiometer. Our main topics for this presentation are: what is an audiometer, types of audiometers, history of audiometer, ear anatomy, hearing test, audiogram, and instrumentation of the audiometer. What is an audiometer? Hearing loss is a thing that generally seen in the people who is older than 50, and the 50% of the people who are older than 80 experience this inability. One way to measure hearing loss is by using audiometer. The audiometry tests how well your hearing functions are. It tests both the intensity and the tone of sounds, balance issues, and other issues related to the function of the inner ear. So what are the things that causes of hearing loss? Birth defects, chronic ear infections, inherited conditions, an injury to the ear, inner ear diseases, regular exposure to loud noises, a ruptured eardrum. The audiometer is an electric instrument which helps to diagnose people with hearing loss. It is consisting of a pure tone generator, a bone conduction oscillator for measuring cochlear function, an attenuator for varying loudness, a microphone for speech testing, and earphones for air conduction testing. Audiometer produces pure tone sounds at specific volumes to each ear to test them separately. Pure tone sounds are signal frequency sinusoidal waves. Sound intensity is the power carried by sound waves per unit area in a direction perpendicular to that area. The higher the intensity of a sound, the louder it is perceived in our ears and the higher volume it has. The device decreases volume of each tone, the patient no longer hears any sound. Now I will talk about the different types of audiometer. There are 4 different types of audiometer, which are diagnostic or clinical audiometer, computer-based audiometer, automatic audiometer, and screening audiometer. Computer-based audiometer uses computers for generating and controlling sound and also storing the patient's response and thresholds. Automatic audiometer is an audiometer which can be used in the situations where there are no direct access to a clinical audiologist, and it can automatically change the signal level based on the patient's response. Screening audiometer is used for hearing screening in the situations where a patient cannot be tested in a clinics. It is smaller in size and portable. The ranges of sounds are more limited than clinical audiometer. As we see in the figure 6, diagnostic audiometer has more types of tests than the other types of audiometer, and that's make it more useful to determine the thresholds and the problems in the ears. So, let's talk about the history of audiometer. Graham Bell's telephone invention was an important invention for the clinical auditory because it was used as a transducer. And in the same years, in 1849, the development of the induction coil, which is used to control electrical stimulus intensity, was also important. Tuning fork, which helps to test at the hearing of the people, is an important place in the clinical auditory, and it evaluates hearing loss by comparing air conduction to the bone conduction. In 1885, Arthur Hartman designed an auditory chart which included the left and right ear tuning fork representations. In 1899, Carl Seashore introduced the audiometer as an instrument to measure the keenness of hearing, which is the ability to perceive sounds of low intensity. And in 1967, Sohmer and Feinmesser were the first to publish auditory brainstem response recorded with surface electrodes in humans, which showed that cochlear potentials could be obtained non-invasively. In 1978, David Kemp reported that sound energy produced by the ear could be detected in the ear canal. And in 1988, the first commercial system for detecting and measuring autoacoustic emission was produced.
Human ear can hear sounds between -15 and 140 decibels, but sounds over 120 decibels damage the human ear. Besides, if we hear sounds over 85 decibels during a long time, it also causes hearing loss. Normal speech sound is about 60 decibels. If we determine sound range in hertz, human ear can hear sounds between 20 and 20,000 hertz. And normal speech sound is in a range between 500 and 3000 Hz. Human ear consists of 3 major parts. First of them is external ear or outer ear. Second one is middle ear, and the last one is inner or internal ear. Outer ear consists of auricle, endoral fluid, and auditory canal. Middle ear includes eardrum, middle ear ossicles, oval window, and eustachian tube. Inner ear consists of vestibule, semicircular canal, the saccule and utricle, cochlea, and corti organ. Let's start with the first part of the ear, which is outer ear. Auricle is the first structure that sounds come from external environment. So sound is collected by auricle. Every fold of auricle guides the sound. Endoral fluid, or it can be said in-ear fluid, keeps moist inside of auditory canal, and it helps to our ear to keep healthy. Auditory canal sends sound waves to middle ear. Middle ear has 4 different parts. First one is eardrum. Sound waves are delivered to eardrum by auditory canal, and it converts these sound waves to vibrations. These vibrations come to middle ear ossicles. Middle ear ossicles consist of 3 tiny bones, which are malleus, incus, and stapes. They strengthen vibrations and send to oval window. Oval window is found between inner ear and middle ear. It takes strengthened vibrations from stapes and delivers to inner ear. Eustachian tube opens the pharynx and provides pressure balance for eardrum. The last part of the human ear is inner or internal ear. It consists of 2 different parts, which are bony labyrinth and membranous labyrinth. As it can be seen in the figure 11, bony labyrinth is outside of inner ear, while membranous labyrinth is within bony labyrinth. Vestibule is the first structure of inner ear, and it touches oval window. Semicircular canal helps to maintain balance of human body. There are 2 structures are called saccule and utricle. These structures include otoliths, which are made of calcium carbonate and responsible from balancing. Cochlea is the third structure of internal ear. It has 3 canals, which are called vestibular canal, tympanic canal, and cochlear canal. Stimulus is delivered corti organ through these canals. Corti organ is the last structure of human ear. It contains hearing nerves called vestibulocochlear nerves. When stimulus reaches here, it is delivered nervous system to be evaluated. This is the map of hearing event. Sound waves reach auricle first. Then it goes to auditory canal, eardrum, and middle ear ossicles respectively. From here, sound waves are converted vibrations and amplified. Then it comes oval window, vestibule, semicircular canal, cochlea, and corti organ respectively. And finally, stimulus is delivered to thalamus, and then it goes to hearing center of the brain.
Diagnostic hearing test is used to measure hearing thresholds of the people. There are 2 different types of tests. One of them is the air conduction test and the other is the bone conduction test. In the air conduction test, sounds need to go through from outer ear to middle ear and the inner ear, so go through all the hearing mechanism. But in the bone conduction test, the headset bypasses the outer and the middle ear and only stimulates the inner ear directly. In the air conduction test, headphone will be used to send the signal which is taken from the audiometer. The signal will be sent to the patient's both ears, but as separately. After the patient wear the headphones, some signals in different frequencies will be sent to the ears, and a patient will press the button whenever he hears the signal. Then the audiometer will collect all the data taken from the test. In the bone conduction test, a bone conductor is used as a headset which fits to the mastoid bone behind the ear. The signals with different frequencies again will be sent to the patient, but this time both ear at the same time, not separately. This determines the hearing threshold of the patient for bone conduction. After the audiogram for the patient is created, it can be seen if there is any problem.
Now we can summarize the variety of tests that can be done in the clinical audiometer. First, I will explain pure tone audiometric air conduction test. The aim of pure tone audiometry is to find the hearing threshold sensitivity. What do we mean by pure tone sound? Pure tones are the signal frequency sinusoidal wave sounds. Hearing threshold is the slightest perceptible sound, the minimum intensity or value of a signal that will respond or specify an effect. It is done by presenting a pure tone to ear through the earphone and measuring the lowest intensity of sound the patient can hear. And also we need to know the intensity of sound. So intensity of sound is the power carried by sound waves per unit area. The higher the intensity of a sound, the louder it is perceived in our ears. The test procedure is repeated by sending the sounds between 250 to 8000 Hz to each ear separately, and the results are recorded to audiogram. In the air conduction method, the sound has to go through all of the ear mechanism. In the bone conduction test, the test is done by placing oscillators on the mastoid bone and measuring the threshold with the same frequencies in pure tone. The mastoid bone bypasses the middle ear and outer ear, and it stimulates the inner ear directly. Sometimes audiologists can add some noise. In this method, the pure tone is not sent to ears separately. The sound is delivered to both of the inner ears at the same time at the same level. If there are differences in both tests, we can understand where the problem lies, because the air conduction test stimulates whole pathway, while bone conducting stimulates inner ear. And that's the goal of the diagnostic test. So we understand that if there is something different in the bone conduction test, we understand that the problem lies in inner ear. Lastly, speech testing. This test is made to see the ability of a person to hear and understand speech. The speech threshold should be within minus plus 10 decibels of the pure tone average at frequencies of 500, 1000 and 2000 Hz. The speech discrimination score is obtained using phonetically balanced one-syllable word, usually presented at 25 to 40 decibels above the hearing threshold obtained from the pure tone audiogram. So in this test, an audiologist gives a word to the patient, and if the patient hears and understands the voice, he or she can say what the word is, and we can understand if she or he can understand the speech. In the figures 17 and 18, we can see audiograms. What can we learn by looking at the audiograms? We can learn the degree of hearing loss, configuration of hearing loss, and type of hearing loss. As you see in the audiograms, the x-axis is frequency in hertz and y-axis is hearing level in decibels. Basically, your hearing levels will be measured at every frequency where they test how many decibels are required for you to hear the tone. There are different marks for different ears and different tests. By looking at the marks in audiogram, we will compare the results by the normal results, so we can understand the degree of hearing loss. By the kind of hearing loss, it is also can be done by looking at the different marks for different tests.
Audiometer aims at determine whether hearing loss exists or not. It also shows degree of hearing loss if exists. It compares results of patients with average hearing values of healthy human. If threshold of patient is 25 to 40 decibel higher than normal, patient has hearing loss in mild hearing loss level. If threshold of patient is 40 decibel to 55 decibel higher than normal, he or she has hearing loss in moderate hearing loss level. Threshold and normal values are compared like that, and degree of hearing loss increases with difference between results and normal values. Names and borders of hearing loss can be seen at figure 19. This is the example data for audiogram. Vertical line shows threshold and horizontal line shows frequencies. In audiogram, left and right ears are represented with different shapes. For example, threshold of patient's right ear is approximately 15 decibels at 250 Hz. And patient has normal hearing at this point. When we look at 4000 Hz, threshold of patient's right ear is 65 dB and he or she has moderate hearing loss at 4000 Hz. Reading of audiogram is like that, and it is same for left ear.
Now we come to the instrumentation of clinical audiometer. As in the figure 21, we can see instrumentation of a clinical audiometer. Firstly, we generate a voice, then it goes to attenuator and envelope. Then the digital signal goes to digital to analog converter, low pass filter, and then it gets amplified so we can hear the noise in the earphones. And now we begin with an oscillator. In figure 22, you can see general block diagram of an audiometer. And to generate a noise, we start with an oscillator. An oscillator generates pure tone usually at the frequencies of 125, 250, 500, 700, 1000, 1500, 2000, 3000, 4000, 6000 and 8000. So what was the pure tone sound as we saw earlier? Pure tone sound was a single frequency sound which was consisted of sinusoidal waves. The oscillator is controlled by some form of a frequency selector switch. As you can see, there are different frequencies for air and bone conducting tests. And you can see that bone conducting test starts with a higher frequency. And now we can see inside of an oscillator. An oscillator is basically an amplifier with a positive feedback. When some input sinusoidal signal is applied to the amplifier, the input signal will be multiplied by the gain of the amplifier. As we see in the figure 23, the feedback signal VF will act as an input of this amplifier. After removing the input voltage, whether we will get the sustained oscillations or not depends on the product of A and beta. A beta is known as the loop gain of the oscillator. Beta defines what fraction of the output voltage is given as feedback to the input. Now we can see a sine wave oscillator. As we know, the pure tone signals consist of sine waves. We can use this kind of oscillator in audiometers. If you probe the output of the oscillator, we can see that we are getting sine wave of 1500 Hz. In the second picture, if we use a capacitor to remove the DC offset of the sine wave and connect it to some earphones, we can hear the 1500 Hz tone. Now, after we generate a sound, we come to the second part, which is attenuator. The amplifiers in oscillator turns the signal to its full-on level, and then the attenuator reduces the signal intensity to bring it back to the desired level. Attenuator controls the intensity level of the signal, usually in 5 dB steps, from -10 dB to a maximum output level that varies by frequency and transducer time. Attenuator is basically the opposite of an amplifier. Amplifier provides gain, attenuator provides loss or gain less than 1. Attenuators are usually made up of simple voltage divider networks, and they are used in circuits to lower the voltage so they do not damage the electrical device, and also to improve impedance matching. Attenuators are generally used in radio, communication and transmission line applications to weaken a stronger signal. As you see in figure 25, there are attenuator types: L configuration, T configuration and P configuration. As you can see, there are basically voltage divider circuits. As we said earlier in the pure tone air conducting test, the test is done separately for each ear. So we need to change the voice signal from between the left earphone and right earphone. In order to do that, signal control is carried out by conventional switching arrangements to directly alter circuit parameters. The frequency selector will switch in appropriately valued resistors to alter the frequency of oscillation of the general circuit. And now we come to envelope of a signal. When doing testing, the audiologist changes the frequency of a signal. And at those points, we have ups and downs in the signal. If the amplitude of pure tone goes to full on and full off, the perception that is, the tone has a popping sound at the start and end. When we are testing hearing, this is not a desirable thing, because we cannot know if the patient heard the intended frequency or some of the additional energy that was created by the tone turning up and down. The outline of the peaks of sine wave form the amplitude envelope. The envelope of a signal is broad, relatively gradual, increases and decreases in intensity of the signal across time. The envelope of a signal can be taken by writing codes. The speech signal in time domain is the envelope of the signal in frequency domain. And as you can see in figure 27, the outline of the peaks of this wave forms the amplitude envelope of the signal. One reason the envelopes of the sound waves are used when illustrating an audiometric signal is, for some audiometer signals, the rise and fall times are quite long, and it would not be possible to illustrate the individual cycles of the pure tone. The longer the rise and fall times, the greater the signal purity. In acoustics, an envelope is the representation of a waveform as a smooth curve joining the peaks of the oscillatory function. When we look at the figure 28, the envelope of the amplitude of the pure tones is outlined. The rise and fall times are shorter in the top figure. The signal illustrated on the top would have greater spectral splatter. And there's another basic image of a signal and its envelope, and as you can see, the envelope outlines the signal. In this page, we can see the last part before the signal goes through the speaker, and it's an amplifier. There is a circuit diagram of LM386 audio amplifier. In this circuit, the volume 10K potentiometer can vary from 0 to 10K, but it is kept as stable about 10K for producing the gain from 0 Hz to 8000 Hz. From this different frequency range can be obtained, which is used for giving the different input to the headphones of the patient. Based on the response of the patient, the audiogram is plotted for the different frequency range.
This figure shows flowchart of diagnosis process. Tone is generated in different decibels and it is tested that patients can hear or not. If patients can, decibel of tone is decreased 5 decibel in each step until tone cannot be heard. If patients can't hear, decibel of tone is increased 10 decibel in each step until tone can be heard. According to results, patients' thresholds and hearing degrees are plotted in audiogram.
For the first question, we have fill in the blanks question. In A part, we are asked, is a structure in the middle ear and converts sound waves into vibration and then delivers this vibration to middle ear ossicles? The structure which does that is eardrum. This is an electronic instrument to diagnose the hearing losses. The audiometer is an electric instrument to diagnose the hearing losses. There are two different types of testing on audiometer. They are conduction test and the other conduction test. In which conduction test the signal is sent to the ear separately, and each conduction test the headset fits into the wishbone behind the ear and the signal is delivered to the which part of the ear for the both ears, not separately. So our answer is there are two different types of testing on audiometer. There are bone conduction test and air conduction test. In air conduction test, the signal is sent to the ear separately. In bone conduction test, the headset fits to the mastoid bone behind the ear and the signal is delivered to the inner ear for the both ears, not separately. Outer ear consists of theory parts and what are they? They are auricle, enteral fluid and auditory canal.
Attenuator helps to reduce the signal intensity to bring it to the desired level. Vestibule is a structure in outer ear that is facing with oval window and it is responsible from hearing. Human can hear sounds between -20 and -200 decibels. In the air condition tests, ears get signal from the audiometer device separately. Auricle keeps auditory canal moist. And the answers are like that. B is false because vestibule is a structure in inner ear that is facing with oval window and it's responsible from hearing. C is also false because human can hear sounds between -15 and 140 decibel. And the E is false because endoral fluid keeps auditory canal moist. Which of the following is not one of the information we can learn by looking at an audiogram? A. Degree of hearing loss. B. Physical information about subject. C. Hearing thresholds for right and left ears. D. Type of hearing loss. E. Configuration of hearing loss. We cannot learn physical information about subject. The answer is B.
Question 4. Which of the following statements is wrong about attenuator? A. Attenuator is the opposite of an amplifier. B. Attenuator controls the intensity level of the signal. C. Attenuators are circuits that usually made up of voltage divider networks. D. Attenuators increase the signal intensity. E. Attenuators are generally used in radio, communication, transmission line applications to weaken a strong signal. The answer is D, because attenuators doesn't increase the signal intensity, they reduce.